Did that go? Yeah. All right, we're in business. All right, last class we were doing partial derivatives and higher order partial derivatives. I hope that that all kind of made sense to you. And we're just going to wrap up this section. There's one last topic here at the end. Had to do with Laplace equations. So the thing that you should understand, this is a math class as opposed to an engineering class. So, you know, Laplace equations are something you deal with in engineering, but in a math class, we just make a mention of it. We don't get deep into it. I just want to kind of point that out. You know, this is more about the theory than it is about the actual application. We'll do applications, but just we won't get heavy into it. So Laplace equation is a specific type of equation that satisfies the following conditions. So if you're given a function of two variables, in this case we're using u of xy instead of f of xy, then any equation where I'm going to use this notation, the partial of u with respect to x twice plus the partial of u with respect to y twice, if that equals 0, then you're looking at a Laplace equation. All right, so what we're going to do is I'm going to give you a function of two variables, and we're just going to ask whether or not it is a Laplace, if this u is a solution to the Laplace equation. So all we have to check is whether or not this is true. Is uxx plus uyy equal to 0? So that's the question. So let's just calculate these partials, second partials. So what's the partial of u with respect to x? Let's start with that one. So what's the partial with respect to x? 3x squared. Okay, that's the derivative of that first term. Plus, now here we're treating the 3 and the y squared as constants, right? So the x is the variable. So the derivative of a constant times x is just the constant. So we should just get 3y squared there. And now we take the partial of u with respect to x again. So we're just doing this piece right here. And that would be what? 6x. That's it, right? Because this is all a constant, so 6x. All right, now let's do the partial with respect to y, and then we'll do y again. So partial with respect to y would be, so this is 0, right? Because that's a constant. And then here, the 3 and the x are constants, so all we're doing is differentiating y squared. So 2y. And that 2 will come out, create a 6xy. And then we do the partial with that with respect to y again, and we get 6x. So now, is it a solution or not? So is 6x plus 6x equal to 0? And the answer is no, unless x is 0. But if x is 0, then the function we're looking at is kind of trivial, isn't it? It's just the 0 function. So in general, this is not true, so this is not a solution to the Laplace equation. All right, now we move on to implicit differentiation. So do you remember in Calculus 1 when you were dealing with explicit versus implicit equations? You'll remember the difference between those? Does it even sound familiar? Yeah. Example would be like this. If you have like y is equal to x sine x, then this is an explicit equation, meaning that you can solve for one of the variables in terms of the other variable. So taking the derivative of this is pretty straightforward. You just take derivative of the left side and the right side and everything works out great. But There were other times where you had implicit equations, something like x squared plus y squared equals 9. Here, you can solve for y, but if you solve for y, you're going to have a plus or minus. So then you're going to have actually two different equations. And so it's not possible to solve for y explicitly. And so we have a different way of taking derivatives here. To take the derivative here, let's say with respect to x, on the left side and right side. Oh, I'm sorry, I forgot to turn that off. Oh, my apologies. Okay. Let me mute myself here. Okay, so take derivative with respect to x here. We would just, do each of those separately. So derivative of that would be what? 2x. But then this is where things got a little weird. You would say, what's derivative of y squared? This would be 2y dy dx. And then here, derivative of a constant would be 0. So we had this idea that when we're taking derivative of x with respect to x, everything was as normal. But when we took derivative of y, we weren't treating y like a constant, right? We were saying y is some function of x, so we have to apply the chain rule here. In this case, 2y, and then the derivative of the base would be this. So this all kind of look familiar? Okay, so we want to see, is there a similar sort of thing we can do when we have three variables involved in an equation, and you can't solve explicitly for one of them? Now, in this problem, we might be able to do it, but I think you would agree it might be challenging to get z by itself, right? Z equals to something with x's and y's. So can we still go about it the same way? So what do you think? Yeah? Okay, so let's take the derivative, and we're going to be using a partial derivative, okay, because we have more than one variable here. Partial of z with respect to x first. Okay, so let's see if you can kind of figure out how this is going to work. Write it down here. 6xy z equals 1. All right, so what do you think the derivative with respect to x is going to be as we move across here? So what do you think derivative of that with respect to x will be? 3x squared, right? Okay, so that's just going to be our normal 3x squared. Now we are trying to find the derivative of z with respect to x, right? And it's a partial derivative. And so how do you think we're going to treat y? As a constant. Okay, we're going to treat y like a constant. So last class we talked about when you do partials on surfaces, like if you go in one direction you have to hold one variable constant. If you go the other direction you have to hold the other variable constant. Same thing's happening here, it's just we can't solve for z. So we're still treating one variable as a constant and the other one as a true independent variable. So this one, as we would expect, this one, 0. Now this is the part that's going to act like that y did just a second ago in that other differentiation. So the derivative of z cubed will be 3z squared. And then this part right here is where we put like dz dx, right? But we're going to put partial of z with respect to x. All right? And then we do plus. Now we move to this. So how are we going to do this? Because we've got x, y, z all together, right?
So we'll just leave y as a constant, take the derivative, and use that as a derivative equation that the product rule.
Yes. Yep. So we're going to have a product rule here. Here's our product. I'm going to kind of put a dotted line. We're going to do a product like that. And this piece right here, when we take derivative of it, we don't have to do a product rule because we're treating y like a constant. So we're going to be taking derivative of this with respect to x times this plus the derivative of this with respect to x times this. So that's our product rule, right? Okay, so let's do that. What is the derivative of this first part with respect to x? This part right here. 6y? right? 6y, and then times z, and then plus, now finishing up the product rule, derivative of this was a derivative of z.
dz over dt.
Yep, so partial z with respect to x, and then times this piece right here, so 6xy, running out of room here. And then equals, we're ready to move to the other side, equals derivative 1, which is 0. Okay? All right, so let me now kind of clean this up. 3x squared plus 3z squared partial z with respect to x plus 6yz plus partial z with respect to x times 6xy equals 0. All right, so that's our implicit differentiation step. We're trying to find what the partial of z with respect to x is, so what would be our next step? Isolate it, right? We need to isolate the partial of z with respect to x on one side of the equation. So this is just going to be some algebra. So the standard procedure on this is to move everything that doesn't have the partial with respect to z, partial of z with respect to x, sorry, to the other side. So I'm going to move that to the other side and that to the other side. And that will leave me with this term and this term on the left side, right? And both those terms have partial of z with respect to x, so I will factor it out. So let me do that all in one step. Partial z with respect to x gets factored out of this, so I get 3z squared. And then I factored out of here also, so plus 6xy. And that's the left side. The right side are those two terms moved over. Right? Last step. Last step, just divide through, right? Take this whole thing in parentheses, divide it out on both sides. So I'll divide this side by that and then this side. So I'm just going to throw it in here. 3z squared plus 6xy. And then it'll cancel on that side out, or it'll reduce out, and that's it. So your partial of z with respect to x is this expression. So let me try and explain what's going on here. You know that example I gave you just a second ago? It was what, x squared plus y squared was 9? Right? Back in Cal 1. The idea here was that when we draw this graph, it was not a function of, it failed the vertical line test, right? But it's still possible to find the slope of the tangent line here. And there's a corresponding x value for that point. And then there's also one down here, right? So even though these have the same x value in two different outputs, you could say, we have different slopes of tangent lines here. So in order for me to ask what is the slope of the tangent line at a particular point, I have to give you not only the x coordinate, but I also need the y coordinate, right? Both the x and y are required for you to find this. What this is saying over here is if you want to know how fast z, which is our up and down, how fast our up and down is changing with respect to x. So if x changes a little bit, how much does our surface go up and down? You're going to need to know what? Not only your x coordinate, but your y coordinate and your z coordinate. So this equation up here might turn out to be some sort of, it's not an ellipsoid, but you know, it's some three-dimensional surface where it would fail kind of that vertical line test again. So to talk about the slope of the tangent line in any direction, any particular direction, I'm going to need to know an x coordinate, a y coordinate, and a z coordinate so I can distinguish it from other points on the surface. Make sense? Yeah. Okay. All right. What about the next part, part B? The only difference there is what?
It's you said it's partial 0, partial x, now partial 0, partial y.
With respect to y, so that means we're going to treat x like a constant in the entire problem, right? And let the y be our standard derivative. So let's just write that one out. We won't go through the step of solving. Let's just make sure we can get the differentiation correct. So I can still start right here. Take a second to do that. If you don't mind, real quick, I've got to respond to this. Apparently this is All right, is that what you get? Okay. So pretty much the same principle, just something else being held constant. How do you feel about that? Okay? Sure? No questions?
I have a question.
Yes.
What allows us to like just make one constant? Is there just I don't know.
Go back to the idea from last class. Remember we had like a surface and we said, okay, let's say we walk out to some point, x, y, plug that into the function, and we're standing on the surface somewhere. And we want to know, like, if I take a step in that direction, like parallel to the x-axis, if I start walking that way, am I going to go up or down? Well, the way we do that is to say we're going to walk in that direction means we're going to hold our y value constant so that we're always on this line. And then we allow our x to change so that we can go up and down. And so we've taken this three-dimensional picture and flattened it down to a two-dimensional picture. Do you remember how I tilted it and we looked at it from the side and it just looked like a curve? That's the idea. We are holding one constant because we want to know what happens as we move in one particular direction. Okay? Holding here is holding y constant. If we do it this way, this holding x constant. The big question will be, what if I want to go that way? Yeah. Right? Okay, that's coming. Yeah. I guess the main difference here is that this is what we do when our surface is not a function of two variables, that it may wrap around itself. And so when you give me an x and a y, you don't know if you're necessarily up here or down below. Make sense?
Yes.
Okay. All right, so that was it. That's it for that. All right, so now tangent planes. Make this a little bigger. All right, so back to the idea that we're going to kind of switch back to what we were doing last class, and that is if z is a function of x and y. So you can solve for z. This is an explicit equation. So if you've got this z is some function of x and y, and f has continuous partial derivatives, meaning if you take the derivative, partial derivatives, both with respect to x and y, they are continuous, meaning there's no weird, division by zero or square roots of negatives. If we've got well-behaved partial derivatives, then the equation of the plane, which is tangent to the surface at some given point, x naught, y naught, z naught, is this formula. All right, so let's try and understand what this is. Hopefully, if you look at this right here, A, B, C. I hope that looks like that equation, that standard equation of a plane. Remember this? That's your standard equation of a plane. So this is saying that if you've got some surface and you go to some point on that surface and you want to know the equation of the plane which is tangent to that, at that surface at that point, then to figure out the equation of the plane, you first of all need a point, right? Tell me where you are on the surface. And that'll give you your x naught, y naught, z naught. But to figure out these coefficients, you're actually going to just use the partial derivatives. So remember, even in this equation, the equation of a line, when we talked about tangent lines, this m was the slope, right? We would say the slope of the tangent line, which is the derivative at that point. All this is saying is that if you take the partial with respect to x, which is, again, pointing in that direction, then we have a slope in that direction, right? And then if we take the slope in this direction, that's the partial with respect to y, somehow those two slopes act like vectors, right? And they create the normal vector of our plane. So the a, the b, and the c, right here, those partials generate our a, b, and then our c is always -1. That's interesting. No matter what, it's always -1. I wonder why that is. Why do you think? if you have some surface that is truly a function of two variables, all right, then if we follow the formula, this is the partial, right, with respect to x at a point, this is partial with respect to y, then following that format, this one should be the partial with respect to z, right?
Yes.
What, are you answering? Go ahead.
This is what I think.
Okay.
Is it because you're treating z as a constant in this form?
Well, z is not really a constant because it depends on x and y, right?
Yeah. Okay.
So it varies as x and y does.
Oh, the fact that you're taking the partial derivatives of that, would it mean you're going from 3 dimensions to 2 dimensions? Those are the two I got. So.
Let's try and, does anyone have another way maybe of looking at it? Think about this again. If this piece right here, right, is holding y constant and seeing my slope that way, right? This one right here is holding what? X constant and going this way. So this right here would almost be like holding, which way am I pointing? Like this was this way, this was this way. What would, if we follow the same format here, which way would that be? Like this? And then asking, my slope is I'm going kind of up and down, right? But because this is a surface, a true surface, my up and down will always be orthogonal to the xy plane. I'm always going to be, like, think again about the vector. You know, the vector 1 in our z component right here. 1 would be straight up, right? And -1 would be straight down. So all this is saying is as long as this surface is a function of two variables, then my up and down motion is always going to be in the direction of the z-axis. It's always going to be straight up and down. It's not going to be ever tilted to the side. I'll clarify this more because we're going to have a more general formula, all right? And once I generalize this formula, I think it'll be a little easier to see that this is -1. I don't know if you look at that and go like, why is it -1? It seems weird. For now, I guess, can we just take it on faith?
Sure.
Okay. All right, so there's our formula, all right? If we can calculate a couple of partials, evaluate, we should be able to find the tangent plane for any surface, as long as that surface is a function of two variables. One more thing. When we say the tangent line to a curve, like if I go to this point, the tangent line means that we just barely touch that curve, right? Just barely touch that curve, almost like at one point, it's like, but it's okay if that line punches through the curve somewhere else, right? It's just like what's happening like locally. Same thing here. If we have a surface three-dimensionally, and you know we got little hills and valleys, if we go to a specific point, we want a plane which is just touching that surface kind of at one point, balancing on that surface. It's okay if that plane cuts through the surface at other places. The easiest example is a sphere, because if you like go to the North Pole, the plane is obviously just a sheet on top of the North Pole, right? But in more complicated shapes, it may actually punch through our shape somewhere else. So just keep that in mind. All right, let's do an example. So here's a surface. Z equals f of x, y, which equals 1/2 x times y. And we want to know the equation of the tangent plane at the point 1, 2, 1. All right, so let's start out. I'm going to write the formula out first. We need to figure out what the partial of f with respect to x is at the point x naught, y naught, and then x minus x naught, and then plus partial of f with respect to y at the point x naught, y naught, and then y minus y naught, and then always minus 1, and then z minus z naught equals 0. We know x naught, y naught, z naught, right? We know that already. That's 1, 2, 1. The only thing we need to do is figure out what those partials are and evaluate those partials. So I'm going to start filling out the rest of this. This is partial of f with respect to x at 1, 2. So all I need for this formula is the x naught and y naught, which are those two numbers. And then here, x minus 1 plus partial of f with respect to y at 1, 2. And then y minus 2 minus 1, z minus 1 equals 0. So that's just plugging and chugging, right? How about some partials? We need them, right? So let's do them over here. Partial of f with respect to x. What's that?
X over and 1/2 y.
Did that seem like power, kind of?
Yeah.
We might get lucky here today. All right. What is this? Half y? Right? Okay, so tell me what that is at the point 1, 2 then. So this is going to be you're kind of pointing in that direction. You're saying, okay, what's my slope? But I need to know where I am, right? So I'm at the point 1, 2. So that means all I'm going to do is plug 2 in here for y. So that's 1. With me? Okay, now we need the partial of f with respect to y. We do that. It's just half x, right? And then we do that at the point 1, 2. So plug in 1 for x here, we just get a half. And then once we have this information, we just come back over here. So this is 1/2, x minus 1, and then plus, wait a minute, yeah, wait, I just messed that up, didn't I? This was the first one. This was 1, and then that next one is 1/2, and then y minus 2, and then minus, I was watching the forecast this morning, they said that it's probably going to rain east of us. I guess this is a new east.
This is the east.
All right. Yeah? So if we graph that plane should just touch our surface at the point 1, 2, 1, and it should be tangent to our surface. And I believe I have a visual for this, so we can just see what we just did. Okay. So there's the surface. This is 1/2 x times y. All right, there it is. And here's I have the computer doing tangent planes for us. I can move this plane around wherever I want on this surface. So you can see at different points, I have different tangent planes, right? And we wanted to go to x is 1 and y is 2. And that's it right there. Wow, that's all messed up now, but I can't even tell where x and y are. You get the idea, yes?
Yes.
Okay, so that plane crosses through that point, is tangent to the surface. So, like, the foundation here is that the mechanical part of this is pretty straightforward, right? You do a couple of partials, you plug in the x and y, write out the equation, you're done. So the only thing that can really become complicated at this point would be the partials themselves, right? Can't do those partials get messy. So here's an example of one that is a little messy. Why don't you take a little time? At least for this one, just calculate the two partials, all right? I'm going to give you a few minutes to do that. And then we'll ask for a volunteer to give us the answer. And if they're wrong, we'll make them go run in the rain for 5 minutes and then come back and see if they didn't clear the cobwebs. Okay, work on those two partials real quick. Hey, Mom, where are you? Okay. Hey, Coral's texting me. I'm in the middle of class and stuff about the movies. Are you sure you want to go? It's absolutely pouring here. Yeah, it is. Yeah, okay, good. Yeah, okay, good. I just, because I know Maddie wants to go, but I'm like, it's like we almost lost power at the college. So, yeah, I would prefer for y'all not to be out on the road. Okay. Okay. Yeah, okay.
And then when she called me, I told her, it's pouring rain over here, and she said it's raining over there too. I talked to Coral too, you know, and they said let's make it another time. So they're fine. They're watching movies at home.
Okay.
The girls.
All right.
Yeah.
Good. Okay.
Okay. Huh?
All right, Mom.
Okay. Well,
Love you.
Be careful.
Okay.
Love you.
Love you.
Okay,
All right.
bye-bye.
Bye. All right, who's gonna do it? Who's doing it? Who's got it? You gotta go run around the room if you get it wrong. I mean, that would be fun though, don't you think? I mean,
I'll probably try to get my clothes dry. So.
no, you have to come in soaked.
No.
All right, so what do we have? Go ahead. What do you got?
For the
Partial of f with respect to x.
the problem is I forgot how to do it. There's no argument can. But
Okay.
I know the product. I know the inside product though. With that, if we do based on the
You want to do, okay, so you want to give me the end part of this then?
the end part of this, yes, I can give you.
Okay, what's the end part?
So the end part of that will end up being, it will end up being 2 group. So it will end up just being y squared for the first part.
Mm-hmm.
Then you'll have plus, and then you'll have 2xy dy dx. Dy dx in this case. Or no, not that. No, just 2xy.
2xy.
Yeah, 2xy.
Good, yes.
I just love
It's all right. Yeah, because we just talked about implicit, so it's a little confusing, right?
Yeah,
But we're
it's
going
a-
back to before implicit now.
Yeah.
Okay, so that's the end. What about the beginning? So what is the derivative of arctangent of anything? 1 over 1 plus whatever the argument is squared. Okay, so there's the beginning.
Okay.
All right? So just you have to remember the derivative of arctangent of x here. So it's ugly, but it is what it is, right? You can't do anything about it. It is what it is. The partial of f with respect to y is going to look very similar, in the beginning at least, the same thing, right? No difference with the first part. It's this second part. So what is the derivative of xy squared? Oh, did we all agree with that or no?
I agree with that.
Sorry, I forgot to ask if we agreed with this.
Shouldn't it be just y squared?
Yeah, so this part right here, again, I think you're doing too much. The derivative of the inside, we are doing the derivative with respect to x, right? Which means we're treating y like a constant.
Oh, that's right.
So this is a constant, right? This is a constant. So the derivative of constant times x is just the constant.
Yes.
So if you did use the product rule, if you were going to use the product rule, that would be okay, but you would get a different answer because the derivative of x here would be 1 times y squared, and then plus the derivative of y squared, which would be 0.
Yeah.
And so you would still at the end wind up with what here? So this part right there is 0. So that should be just y squared in there. Sorry, I should have pointed that out. I was thinking about you running through the rain. And so, okay. And then here, what would the part of this be? 2xy. Okay, so now you're treating x like a constant, taking derivative of y squared, so 2y squared. All right. Now, where am I going to need to evaluate this first partial for my equation? At 1, 1, right? And then I'm going to need to evaluate this one also at 1, 1. So let's see what we get when we evaluate this at 1, 1. 1 is all 1 squared, and 1, 1, 1 is just a half, right? Okay, that's a half. And then here, We get 2 here on top, and then we get a 2 on the bottom, so this should be 1. So the equation of our plane should be that partial with respect to x evaluated at 1, 1, so 1/2, and now just x minus x naught, and then plus this one, 1, and then y minus y naught, and then what is this one always? -1 times z minus pi over 4 equals 0. There we go. Okay. All right, I think I have a picture of this one. I have a picture of this one just because I think the surface is worth looking at. Like the surface is kind of interesting. Does this function have any domain issues? Does the arctangent function have any domain issues? Does it? Yeah, so arctan is the inverse of tan, right? Tangent has domain issues. But what is the range of tangent? So think of the tangent function, right? It goes like this. Right, it's periodic, keeps doing this, but it's between negative pi over 2 and pi over 2, right? And then it just repeats itself. Every pi, it has a period. So the domain of tangent is restricted. You have domain issues, but the range is all real numbers. So when you look at arctangent, the domain and range flip places, right? So the domain of arctangent is all real numbers. So we have, when we sketch this surface, we should have picture everywhere. We shouldn't have any sort of asymptotes or any sort of craziness happening. There it is. Okay, so here's the picture right here. That's your picture of your arctan of whatever that thing was. And so we went and found at that particular point, there it is. We found the equation of that tangent line, or tangent plane that touches the surface at that point. And that's it for tangent planes. That section's pretty straightforward. Like I said, it really is just going to come down to more, you know, the partials. Are you going to be okay with those partials? That was 11.3, correct?
That was 11.4.
Was it 11.4?
I think so.
I think you're right. Just want to make sure I'm not getting out of order here. Yeah, okay. So now we go to 11.5. And 11.5, I have a different set of notes for 11.5. So let me get those up here. All right. Yes. The chain rule. I mean, we're working our way through this, aren't we? I mean, we are, it's kind of like Cal1 revisited, you know? All right, so we got to do the chain rule. So let's remember some stuff we already learned. And the way I'm going to put this up on the board, it's almost going to be like, why are you making this look so complicated? It doesn't have to be this complicated, but it's because it'll help. I think it'll help us as we proceed. Okay, so remember that if y is a function of x, so something like y is equal to, let's say, x sine x, right? Y depends on one variable x only. Then we only have one derivative really possible here. If y depends on x, the only thing that we can really talk about is this derivative, dy dx. We could also do dx dy, but if we're saying y depends on x, then this is our standard derivative, right? dy dx. So the way we could write this is put y here, because y depends on x, put x down here. So if you give me an x, I can tell you what y is. And then I create this branch that goes from y to x, and the only derivative possible down that branch is dy dx, right? That is water.
It is a lot of water. Yeah.
Sorry, I'll be honest with you.
Yeah, oh, move, move, move. It's coming through. Wow. You may not have to go run in the rain. You may just have to sit in class. Wow. Okay, well, I guess you might want to move.
Class is over for you.
Wow. Yeah, I mean, you maybe the other side, or y'all can rotate the table or something. It's probably not a good thing to have water up there and there are lights and speakers and stuff. Is everybody grounded? Make sure you're grounded. Yes?
We're all grounded.
All right, so now let's look at our chain rule from calculus. What's going on? I know, right? At least it gave you a warning, right? At least we had some indication. So I got to tell you a story. I was coming back from Florida I forget. I was in Florida a couple of months ago, and I had a very good water bottle that had a little flip cap that opens up and you drink out of it, and it has like a straw that goes down to the bottom. So I had my water anyway. I got on a plane, right, and we're up at altitude, and I go to flip the little thing open to take a drink, and the pressure was now different, and this thing like blew up in my face, like water started spewing out, but the thing flipped open like straight up, and it went and created this arch and went right on the lady in front of me. I mean, just right, and I freaked out because it like hit the overhead and then like started showering down on her, and I freaked out. And I closed it, and I don't know why, like I opened it again, and oh my God, she was so pissed off at me. And I'm sitting there trying to explain to her, like, I'm sorry, like pressure, like, can you imagine just sitting there on a flight, and then all of a sudden you start just getting rained on? It was hilarious. One of the highlights of our trip, though, we like, because my family was all in the same row, and everyone was just laughing at me. Let's try this again. All right, so what this is saying is this. When we have composition in Cal 1, like something like, let's say, sine of x squared plus 1, right? This is a function inside of another function, right? So what we could say here is that y is some function of x, but x is some other function of t. So let's see if this makes sense. If I replace, if I were to say sine is a function of x, but x is this, then that basically goes in there and we get this, right? So if we put the composition together, we get that. So here, our chain looks like this. We have y depends on x, and then x depends on t. And if we do it that way, then to get from y to x, we have a derivative dy dx, and to get from x to t, we have another derivative dx dt. So dy dt, to get from here all the way down, requires that we go through the whole chain. We go through the whole branch here. We go first this derivative, and then we multiply times this derivative, right? And that's our chain rule from Cal 1. Does it look right, or does that look too messy? Y'all are like.
Just weird to be explained like that.
Yeah, so let me just show that same example. I'm gonna move this up just a little bit. So let's do it this way. Y is sine of x, and x was t squared plus 1. And let's remember where this came from. This was y equals sine of x squared plus 1. Maybe it'll be best if we just take the derivative of this right now. What's dy dx here? So just use your standard chain rule here. Cosine x squared plus 1 times derivative of what's inside, 2x, right? So that's the derivative. Chain rule says here what we could do is we could first, to find dy dt, which would be all the way through, we could do the derivative of this with respect to x first, which is what? What's the derivative of that with respect to x? Cosine x. And then the derivative of this, x, with respect to t, which would be 2t. And then if I multiply these two together, right? Let's multiply those two together. We get cosine of x times 2t. But what's x? T squared plus 1. So this is cosine of t squared plus 1 times 2t, which is essentially the same answer as this answer, right?
Yeah.
So that, again, is chain rule from Cal 1, just kind of in a different sort of perspective. But what do we do if we have a function of two variables? I've been teaching here for a long time. This is the first time I've had water dripping down the classroom. This is kind of exciting. All right, so what if, now we're saying, what if we have a function, z as a function of two variables? Then do you agree that z, the only way for me to ever know what z is if somebody tells me what x and y are, right? So z depends on two things. So my picture looks like this now. Z depends on x and z depends on y. And so now we have two branches, don't we? And when you go down a branch, notice that this is a partial derivative now. And that's because there are two things required to give you z. When you take this derivative, you have to hold that one constant, right? You have to hold that constant to take this derivative. Or if you want to go down this branch, you have to hold this one constant so you can take this derivative. See, everything before this, our branches just went straight down, didn't they? This is the first time that we branch out like that. And because of that, we have partial derivatives instead of the direct or straight derivatives that we had from Cal 1. So I'm not going to do that. Okay, so now look at this. What if our z is a function of x and y, but our x is a function of t, and our y is a function of t? So it looks like this. Z depends on x and y, but y depends on t, and x depends on t. Then in the end, in order to know z, what do you need to know? Just t, right? Just t. Because if someone gives you t, you'll be able to get x, right? And y, and then you'll be able to get z. So what derivative is possible here? That's the question. In the previous example, two derivatives are possible, right? Two different partials are possible because it depends on two different things. Here, since z depends ultimately on t, there is only one derivative possible. And that would be the derivative of z with respect to t. So look at the notation here. Why is it not a partial? Sorry, that is a typo. That's supposed to be dz dt. Please note that. That should be t. That's the only derivative possible. Why is it not a partial derivative? Because it depends on t only. You don't have to hold anything constant to get it, right? You don't have to hold some other variable constant to get this. Does that make sense or not?
Yep.
But look at what the definition of the derivative is. If you want to know the rate at which z changes with respect to t, so if we change t down here just a little bit, what is the impact up there? Then what you're going to do is take the partial of z with respect to x times dx dt plus partial of z with respect to y times dy dt. So do you see where those pieces are here? Yeah. It's this branch, right? Multiply down that branch. Add to that, multiplying down this branch. And that will give you the rate at which z changes with respect to t. We're going to do an example here. Anybody thirsty? No? Give a refill here?
I like the
Okay, so let's do this example. All right, so we have z is equal to x sine of xy, x is equal to t squared plus 1, and y is equal to natural log of t. So when we look at this, we tell ourselves, first of all, z depends on x and y. X depends on t. And y depends on t, like that. Right? So now I'm going to define the types of derivative down each of these branches. So going from z to x, that derivative has to be a partial derivative, because to do this derivative, I have to hold that y to be constant. So this will be partial z with respect to x. But going from x down to t, I don't have to hold anything constant. So this is just your straight regular derivative. So this is dx dt. This one will be partial of z with respect to y, and this one will be dy dt. All right? So to find dz dt, I could memorize the formula, but I think it's better if you look at the tree here. You're going to do down this branch multiplied, and then add down this branch multiplied. So partial z with respect to x times dx dt plus partial z with respect to y times dy dt. I was out of town this weekend, and I had to sleep at my brother-in-law's house. And I'm one of those people who needs white noise in the background. So I have an app on my phone that you can have like ocean sounds or rain or whatever, you know. That's what I'm thinking of. This would have been nice to sleep to. Nice little cavern. This is cavern. This is a cavern sound. Yes. Yes, this is cavern. Just need a little bit of an echo, you know. All right, partial of z with respect to x. So let's get this. Okay, so you look up here. You're going to take the partial of this with respect to x, which means you're going to treat y like a constant, right? Okay, let's do that. Unfortunately, I believe we need to do product rule, don't we? Because they have an x here and an x here. So we got to do a product rule. So that will be, let me do this all in parentheses here. This will be sine xy plus, so all I did there was took the derivative of this times this, and then plus, what's the derivative of sine xy? Cosine xy, chain rule here, cosine xy, derivative of what's inside with respect to x. Just y, right? The derivative of the inside of this, holding y to be constant, is just y. And then you have to finish off the product rule, which is derivative of x. I mean, sorry, not derivative, times x is what I meant to say. That all right? That's just this, right? Yeah. Then I multiply that times dx dt. So I come over here, here's x, right? Okay, here's my relationship. I need to take derivative of x with respect to t. So that is what? 2t. All right? So now I've done this part. So I say plus. Now I take the partial of z with respect to y. So I need to come back here, take the derivative of this with respect to y. Now I don't have to do product rule, right? Because I'm holding x to be constant, so that's just a constant. So what do I get here? X cosine of xy times derivative of what's in here with respect to y, just x. Okay, so that right there is this. And finally, dy dt, what's the derivative of y with respect to t? 1 over t. Derivative of natural log of t is 1 over t. All right, so this is our derivative using the chain rule. The next step, and this step would suck, okay, would be to go back and everywhere you see an x, replace it with what? T squared plus 1, and everywhere you see y, a natural log of t. So you got to do that here, 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 here. And then everything would be in terms of t, wouldn't it? And then your change in z with respect to t would be a function of t. I'm not going to do that. I trust that everyone could go replace all your x's and y's with that, right?
Yeah.
The important thing here is looking at the problem, creating, this is what we call a tree diagram, creating your branches, and then putting them together, all right? I'm just curious on the, I mean, it is pouring out there. This is like flood type situation here for driving. Wow. I parked in the garage today. I'm glad I did. Okay, just out of curiosity, and I don't even know if this notation is going to make sense to you, or Cal1, if you're taking derivative of a product, how many of you learned that this way? That's f prime g plus g prime f. How many of you learned it like you take derivative of this one times that one plus derivative of this one times that one? Or maybe you learned it like flipped, but okay, how many of you learned it that way, yeah? How many of you learned it this way, where it's like f g prime plus, I don't know, g f prime? Anyone learn it that way? That way? Or any other variations of this?
Prime FG.
What are you, what do you?
Prime FG.
Prime f? Oh, prime. I mean, sometimes it'll be like g prime f plus, I don't know, f prime g. I'm just curious because in a lot of textbooks, at least, well, in the textbook here, I'll tell you right now, the way they show it, I forget, but this always boggled my mind because almost every textbook does this way. Where is it? This particular book teaches it this way right here. That way right there. Okay? That's the way this book teaches it. Which is fine. I mean, it's correct. But here's why I have a problem with this. Because what about the quotient rule? So this book does this. It does g f prime minus f g prime over g squared. That's the way it does the quotient rule. And do you see why I don't like that, or no? Yeah. See, because this, right, to me, when I was learning it, like I learned it that way and then this way, and these almost look like completely different formulas, like they're completely different animals. But if you learn it this way, then this is the same formula. See, you can just flip these over, flip those over. So that's f prime g minus g prime f over g squared. So if you learn this product rule this way, the only difference between these two formulas is a minus and dividing by g squared. It's the same thing. So whenever I'm sitting here and I do product rule, I'm always going to do it this way because that's the way I teach it. That's the way I learned it. I mean, that's not the way I learned it, though. So I know some of you do it this way. Doesn't matter. Cal1, that's in the